When I turn on this switch, an electric current starts running and our fan spins. Such devices which convert electricity into rotation, we give a name to it, we call it the electric motor. And these devices are used in many places, like in your washing machines, your drilling machines, or even your electric cars. But the big question is, how does an electric current, which is basically moving electrons, push something as big as a fan and make it spin? The secret to these motors are magnets. In a previous video, we had seen that a current carrying wire can be pushed by magnets, or more technically, magnetic fields. So an electric motor uses this magnetic push to spin a current carrying conductor. So in this video, let's explore exactly how it works. So let's start with a couple of magnets, which will generate a magnetic field that's going to push our current carrying wire. And instead of just introducing a single wire carrying current, we will introduce a current carrying rectangular loop. Now the loop can be of any shape, but if you take it as a rectangle, it'll be easier to analyze this. And if you're wondering why are we considering a loop, we'll soon understand why. And as of now, let's not worry about where the current is coming from, where the battery is. We'll deal with that later. Now, each side of this rectangular loop is a current carrying wire inside a magnetic field. That means each side will experience a force. And as a result, this coil might start moving. Now, to figure out how this coil will move, we need to figure out the direction of the force acting on each side of this loop. And to do that, we've seen before, we can use the left hand rule, where you take your left hand, you stretch your fingers like this. I remember FBI, the thumb gives the direction of the force, the forefinger gives magnetic field, and the middle finger gives us the direction of the current. So to figure out the force on any side of the wire, we just have to align our fingers in according to the current and the magnetic field, and the thumb will tell us what direction the force is. And so what we need to do next is apply this left hand rule to each side of the wire. And so can you try and do this yourself first? So great idea to pause the video and see if you can apply this yourself and figure out the direction of the force. All right, let's do this. Let's start with the pink wire. The current is inwards and the magnetic field is to the left. So if we align our left hand, it will look somewhat like this. And so notice the thumb is pointing upwards, and as a result, the force is upwards. Now, if we apply the same left hand rule to this side, we see that the force is acting downwards. And if you look at these two remaining sides, the current is parallel to the magnetic field. And we've seen before, whenever our electric current is parallel to the magnetic field, the field does not push it. And so there'll be no forces acting on this wire or on this wire. So there'll be an upward force here and a downward force over here. And as a result, our coil will start moving. But how exactly will it move now? Well, here's my board. Let's imagine this is our rectangular coil. Notice on the left side, I'm going to push it up. On the right side, I'm going to push it down. And as a result, notice it starts spinning. So just like this, our coil will also start spinning. And in fact, over here, it's going to spin in the clockwise direction. So the same thing will happen over here. Our coil will start spinning in the clockwise direction. Now, as it spins, the forces on this wire and this wire will remain the same because the magnetic field is still in the same direction. The current is still into the screen over here. That has not changed. So the force over here will still be up, and the force over here will still be down. But if you're curious, You may wonder what happens now to the forces on this side and this side. Earlier, they were parallel to the magnetic field, but now they are no longer parallel to the magnetic field. So won't there be forces acting on these wires now as well? Yes, there will be. Won't those forces affect our rotation? No, they won't. Why not? Let's see why. Well, if we apply the left-hand rule to this wire, notice the magnetic field is to the left. The current is sort of downwards. So if you apply the left-hand rule, we see that the force will be into the screen. Now similarly, if we apply the left-hand rule on this side, over here the force comes out of the screen. So there are forces acting on these wires, but what are these forces doing? They're just pulling this coil apart. It's just like taking this board and pulling it like this. These two forces are not going to do anything. They're just going to cancel out. They're not going to provide any rotation. And as a result, we can totally ignore these forces. They will not affect our rotation at all. So throughout the entire rotation, we will ignore the forces acting on this side and this side because they're just going to cancel out. They will not affect our rotation. So yay, our coil is now spinning. But pretty soon we run into a problem. You see, if we bring back our board, if we want this board to continuously keep spinning in the clockwise direction, let's say, then notice the force on the right must always be down and the force on the left must always be up. It should always follow that rule. Over here, once the pink wire comes to the right, notice the force on the right side has become up and the force on the left side has become down. This will spin my coil back in the anti-clockwise direction. So you know what's going to happen next? Next, my coil will spin back like this. Now again, the coil will spin forward in the clockwise, anti-clockwise, clockwise, anti-clockwise. This is bad. This is not a motor, or at least not a good motor because it's not completing even a single rotation. So how do we fix this? Well, to make sure it continuously keeps spinning in the clockwise direction, we have to somehow make sure when this position comes, the force on this wire should become downwards and the force on this wire should become upwards, right? Only then it will continue spinning in the clockwise direction. So we need to reverse the direction of the forces. But the question is, how do we do that? Well, again, let's bring in our left hand. So to reverse the force, say over here, we want the thumb to point downwards. Now there are two ways to do that. One, we can reverse the forefinger, that is the magnetic field, keeping the current same. That's one way to do that. But we'll not do that because flipping the direction of the magnetic field is not all that easy. We have to change the poles and we cannot do that automatically. But another way in which we can achieve this is we can keep the magnetic field the same direction, but we can reverse the direction of our middle finger, our current, like this. And as a result, our force will now point downwards over here. So if we flip the direction of the current everywhere, then the force direction will change everywhere. So the force over here will be downwards and the force over here will be upwards. And if you're wondering, well, how can we change the direction of the current just like that? We'll see how to do that a little bit later. But that's the most important thing over here. In this position, we have to change the direction of the current. So let's get rid of our hand, flip the direction of the current, and now the forces flip, and as a result, our coil will continue to spin in the clockwise direction. Yay! This will happen until, again, once the blue wire flips over. Now once the blue wire comes to the right and the pink wire comes to the left, again we have the same problem. Now again on the right hand side the force is up, left hand side the force is down, and again we need to do the same thing. We need to change the direction of the current. Here it is, change. Once we change the direction of the current, the coil will continue to spin. And so by changing the direction of the current every half a rotation, the direction of the forces will change and our coil will continuously keep spinning. Finally, we have converted electricity into rotation. Now, of course, in this animation, I'm pausing every time the current is changing so that we can see the forces flipping. But of course, in reality, the thing will keep on spinning continuously. The last thing we need to explore is how do we attach a battery to this and make sure that the current direction reverses after every half a rotation. So let's say we bring in our battery, attach a couple of wires to it, and let's say we directly attach these wires to our coil. Then, as the coil starts spinning, because the current starts flowing through it, you will see that the wire starts twisting and tangling and whatnot. But now, more importantly, at this position, we want the current to reverse. How do we do that? Well, we could either flip the battery, or we could flip this connection. We can make this wire come here and this wire come here. Then the current direction will change, the forces will reverse, and the coil will continue to spin. But how do we make this happen automatically? That's the question, right? How do we make it automatic? Well, it can be done by using a device called a commutator. A commutator consists of split rings, which are basically two half metallic rings with some gap in between, and a couple of carbon brushes. So the wires are attached to these brushes, and these brushes are just in contact with these rings. They are not connected to them. Because of the contact, electricity starts flowing through it, and as the coil spins, notice the ring spins with them, but the brushes just stay there. So the brushes are literally brushing against the rings, maintaining the contact and making sure the electricity flows through. This solves our problem of wires tangling and everything. But now, more importantly, let's see how this reverses the direction of the current every half a rotation. So right now, the pink ring is in contact with the positive terminal, and the blue ring is in contact with the negative terminal. But notice what happens once the coil spins enough. Once the coil spins and comes to this position, now notice the pink ring has come in contact with this brush, the negative terminal of the battery, and the blue ring has come in contact with this brush, the positive terminal of the battery. So now notice, due to this commutator, automatically current will start flowing from here into this coil in the reverse direction, coming out from here into the negative terminal. And so the current direction flips, and so the forces also flip, making sure the coil continues to spin in our clockwise direction until again, notice, now again they will change contacts. Now again the pink will come in contact with the positive terminal, the blue will come in contact with the negative terminal, and as a result the current will now again flow this way, again reversing the direction of the forces. And so using a commutator, we have now achieved complete motor action. So what did we learn in this video? Well, we learned that a motor consists of a couple of magnets and a current carrying coil. The magnetic field pushes the coil, making it rotate. And the important thing is, every time our coil comes perpendicular to the magnetic field like this, we want the current to change directions. That is achieved by a commutator, which is basically two split metallic rings and a couple of carbon brushes. So changing the current changes the direction of the force and ensures that the motor keeps spinning in the same direction. And so this is how we can now convert electricity into rotation. And if we have enough current in this, and if the coil and the magnets are strong enough, then we can attach anything we want to it, like a fan or washing machine, electric drilling machine, and make it spin using electricity.